One of the main things that we've noticed since the beginning of the course is that the periodic table of the elements is organized by increasing atomic number. The periodic table has a huge amount of information stored on it, from everything from atomic number to atomic mass, and many other features that we're going to talk about in this pre-lecture. The periodic table is laid out in such a way that trends in periodicity can also be observed. We're going to talk about a few of these trends, and we need to understand why these trends exist. These trends can be explained using two main concepts. One is electron shielding, and electron shielding is something that increases as we go from the top of the periodic table to the bottom. We also have a second type of trend called nuclear pull, or effective nuclear charge, and it's symbolized by this symbol ZEFF, effective nuclear charge. If we have a good understanding of these two concepts, we will be able to explain all of the trends that relate to the periodic table. So let's first look at this concept of electron shielding. In order to explain this concept, we're going to start with lithium on the top left-hand corner of the periodic table. So electron shielding involves increasing n levels. We've talked about already the principal quantum number is n. So let's first consider lithium in n equals 2, the second row of the periodic table, with an atomic number of 3, meaning it has 3 protons in the nucleus. We know that lithium has 2 n levels and 3 electrons. We fill up the first n level with 2 electrons, and the third electron goes into n equals 2. Let's now consider how each one of these electrons feels the pull of the positively charged nucleus. These 2 electrons, which are closest to the nucleus, which we call core electrons, feel the pull of the nucleus the greatest. There is nothing standing in between the positively charged nucleus and this electron or this electron. That means that both feel the pull the strongest, and they each feel a pull of +3 acting on each electron. On the other hand, this electron is further away from the nucleus, and there are 2 electrons shielding the nucleus from this electron in the outermost shell, which we call the valence electron. It feels a weaker pull of the nucleus because these electrons shield the positive charge. We say then that lithium has a total of 3 electrons, but 2 electrons are considered core electrons, the electrons that are responsible for this shielding effect. If we subtract the total core electrons from the total number of electrons, we get an effective nuclear charge of +1, or an effective nuclear charge that's acting on the valence electron of +1. What happens if we move down the periodic table to potassium? Potassium has an atomic number of 19, meaning there are 19 protons in the nucleus. So its valence electron can be found in n is equal to 4. If we fill up these 19 electrons in the orbits of potassium in first n equals 1, then we fill up 8 more in n is equal to 2, then n is equal to 3 holds up to 8 more electrons. We now have drawn on the screen, we have a total of 18 electrons. 18 electrons that we consider to be core electrons, or non-valence electrons. We add the 19th electron to n equals 4, and we consider this electron to be the valence electron. Now let's look at the effective nuclear charge that acts on this electron. Again, we have a total of 19 electrons minus 18 core electrons to give an effective nuclear charge of +1. You'll notice in potassium we have many more electrons shielding this one electron from the nucleus. Now let's see what happens as we go from left to right in the periodic table. We've already talked about lithium and it having an effective nuclear charge of +1. If we march across the periodic table to fluorine, which has an atomic number of +9, there are again two n levels. N equals 1 considers the core electrons. And again, like lithium, there are two of them. We still need to add 7 electrons to give us the total number of electrons that we will need in fluorine. When we add these, we now consider the effective nuclear charge. The effective nuclear charge now between this valence electron or any other valence electron is now much greater than what we saw for potassium. The effective nuclear charge is still calculated the same way. There are a total of 9 electrons minus the 2 core electrons that are now shielding the nucleus from the valence electrons. Now there are only 2 core electrons, so the electrons in the valence shell feel a stronger pull from the nucleus. They feel an effective nuclear charge of +7. Now, knowing these two trends now, the trend for increasing electron shielding as we go down the periodic table, and the increasing nuclear pull as we go from left to right in the periodic table, we can explain trends that are observed in the different atoms. First, consider the trend in atomic radius as we go down a group in the periodic table. If we consider lithium and potassium, both group 1A elements, or alkali metals, we see that the effective nuclear charge remains constant. What's different, though, is the number of n levels and the number of shielding electrons. As we can see, the atomic radius of lithium is much less than that of potassium. That's because of the increasing number of n levels and the increasing number of electrons that shield the positively charged nucleus from the valence electron. Going from left to right in the periodic table, we also see a trend in atomic radius change. Now it's the effective nuclear charge that plays the greatest role in determining the atomic radius. The number of core electrons remains the same in each case, but the valence electrons feel a larger nuclear pull in the case of fluorine. The atomic radius of lithium, as we saw earlier, is 152 picometers. But what happens with a greater effective nuclear charge or a larger nuclear pull from the nucleus is they pull the valence electrons in closer. So the atomic radius of fluorine is now much less than that of lithium. So what have we learned from this pre-lecture? We've noticed that increasing electron shielding occurs as we go down the periodic table, and this results in an increasing atomic radius. The nuclear pull, or the effective nuclear charge, increases as we go from left to right. This means that the atomic radius must increase as we go from right to left in the periodic table. Electron shielding and nuclear pull are two concepts that will explain all trends in the periodic table. Just keep in mind that right now in this pre-lecture we're only showing how it affects atomic radius. Try and use these two concepts, electron shielding and nuclear pull, to explain other trends in the periodic table that you will learn about.